I'm Michael Sullivan, and in addition to being on Dropbox, I'm one of the core developers of the mypy project, which is an open source type checker for Python that that Dropbox uses heavily and contributes a lot to its development. So what this talk is going to look like is it's going to be a quick overview of Python typing and what mypy does. Then we'll talk about what we did at Dropbox to get code annotated and what lessons people might be able to take from that. And then we'll talk about some of the problems that our success caused us and how we kept up with them. So mypy is an optional static type checker for Python. Python 3 added syntax for adding type annotations to functions, and Python 3.6 added syntax for annotating variables. And mypy allows you to use these annotations to actually statically check that the program works, or that the program follows its types. So here's the basic first example from our website, which is giving the type of a Fibonacci generator that yields all the Fibonacci numbers. And here it's just annotated, or yields the first n rather. It's annotated that it takes an integer and that it returns an iterator of ints. And it sees that when we're yielding ints, that means that it works as an iterator of ints. The sort of basis for all of this work is PEP 484, which is a PEP that sort of defines what static typing should mean in Python and adds a typing module to the standard library that includes things such as iterator and list and sort of all the core building blocks. While I talked about using Python 3 and the syntax it adds for it, obviously, unfortunately, it's still important to support Python 2. And so it supports Python 2 perfectly well. It's just ugly. You write these type comments that say type : and then an annotation. And this is basically how we have to use everything at my employer still. Showing you examples of code that works, as in the previous slide, is all fine, but really the main value of a type checker is when you hand it code that doesn't work and it tells you that it's broken. And so here, if we have some function foo that takes a stir as parameter and we try to call this eggs method on it, it will happily inform us that stir has no attributes eggs, which is nice because it doesn't. And a somewhat more subtle thing is differently from many languages, like traditional statically typed languages like Java, if you pass in none when you expect a stir, that's also an error. You can't put in sort of a null pointer in arbitrary places. You need to sort of declare that. So that's a big difference from some of the traditional systems. One thing to note is that mypy is a totally static tool. It doesn't run the code to do any of this. It does all of these analyses sort of just on the source code without running anything. Now, since Python is traditionally an untyped language, it wouldn't work if you just said, OK, we want to use a type checker now, so the first step is you type annotate all your code and then you run it, because people would say, actually, I'm not going to do that, because there's too much of it. And if we aren't getting value while we're doing it, there's no point. And so mypy is what's called gradually typed, which allows you to somewhat seamlessly mix typed and untyped code. And when typed code uses untyped code, it just assumes that it can do anything. It just doesn't worry about it. So here we've got an untyped function bar and a typed function foo. And we can do things like make sure that we call it with the right number of arguments, but it won't know anything about what the details are, what types it actually needs. So given sort of that background, what do we actually do with this? How do we sort of get it rolled out at Dropbox? So one of the first questions that you might ask, and some people at my employer have asked of us, is why bother? Maybe it's not worth it to get this old code annotated or to annotate code at all. And why not just annotate the new code? And the answer for that is, why not just annotate the new code, is because interactions with untyped code can't be checked. And so the more of a code base is annotated, the more benefit typing gives. It sort of is a positive feedback loop. The more you have typed, the more valuable typing is, and so the more it's useful to type the rest. And as a sort of anecdotal example, in mypy itself, since we're basically 100% typed, we can rely on typing to drive aggressive refactoring. If you rename something, if you move things around, if you refactor interfaces, the type checker will find all the call sites and tell you when they're broken. You don't need to track down all the failing tests, and maybe you don't need to track down all the corner cases if your test coverage isn't as good as it ought to be. Another big thing here is that Python 2.7 reaches its end of life at the end of this year. And I can tell you that Dropbox isn't going to be off of Python 2.7 quite then, but it's recognized that we have to be. And one of the big pain points, the reason it's not just easy, is because converting to Python 3 requires major changes to how you handle string operations. The whole Unicode byte story is very different. And we've found sort of historically that having type annotations is a huge benefit in finding all of these corner cases and all of the places where you're doing something wrong with stir and bytes in Unicode in the transition from 2 to 3. And so a huge part of our strategy for converting to Python 3 is actually increasing our type annotation coverage so we can use that to drive parts of the transition. So how do you get old code annotated? Well, to quote one of the senior engineers at Dropbox when we asked for his advice, and this is despite him sort of not believing in types anyways, but he gave some good advice, which is show value, reduce friction, encourage the general virtuous cycle, which I talked about a bit earlier, is typing makes you want more typing. And when all else fails, move the mountain yourself. So I'll talk about how we did some of those things. So one of the first things we did as part of this is we make sure to talk to our users. We put out regular surveys every quarter or 2 quarters or so to try to get a pulse on what the engineers at Dropbox think about the tool we build. And sort of gratifyingly to us, the 2 biggest complaints, there's usually every survey, there's like one person who says typing Python is a terrible idea and you should not be doing it, and like, we are wasting our money by employing you. Which, okay, but that's rare. The biggest complaints we get is not enough code here is type annotated. We would like more code to be annotated, and performance. We wish mypy was faster so we could run it more, or at least not need to wait for it when we're trying to land code. On top of that, we would have a lot of meetings with teams to try to figure out, like, hey, why isn't your code annotated? What can we do to help? And one answer we get a lot is, well, our big core library can't be typed well. And it turns out if you're designing code to be typed, usually you can design a nice typed interface, and it's not too hard. But if you've designed interfaces sort of not thinking about what the static types would be, sometimes it's not straightforward or even possible to directly map what you're doing into the PEP44 mypy type system. Dropbox's internal database layer, like our abstraction for dealing with databases, is just completely untypable. But mypy has a plugin system. So we can build plugins so that your core library that can't be typed well sort of can be, because we can look at information that the type system doesn't understand and do some logic and produce something good. So we've done that a few times, including for the database layer I was complaining about. And then another excuse we get a lot is like, well, we'd like to type annotate our code, but we're a platform team, and none of the people who use our platform have been complaining to us about type annotations, so it's not on our roadmap. And well, they complain to me about not having type annotations. So one thing we do is we try to make sure that people who have complaints about particular platforms missing type annotations, know who the right people to talk to is, know who to complain to get it on someone's roadmap. So then once we're trying to add annotations, there are a bunch of questions that you sort of need to answer, which is like what annotations are worth focusing on. And it turns out that not even if they show up similarly in coverage metrics, what percentage of the code is covered, not all annotations are worth the same. If a function is called 1,000 times, it's much more important to annotate than if it's only called once. Because if you change it, there are a lot more call sites that will break. And also, if a function is called 1,000 times, probably it's going to be called more times, right? Probably there'll be more places added, and so catching new bugs introduced is more important than if there's only one call site, which maybe it'll only ever have one call site. And so when a function misses annotations, it reduces the value of type checking in every function that calls it. And so fixing those is important. There's a frustrating corollary to this, though, which is that the most important functions to add type annotations to are often the hardest to add annotations to. Because if some function is called 1,000 times and maybe 100 of the call sites have a type issue, then before you can add the annotation, you need to go fix all those call sites or add ignores to them, which people get annoyed by. And so there's a frustrating tension there. But I think the main trick is to power through it and to be willing to say, OK, we don't need to fix all these issues. We can ignore them and rely on the benefits for future code, even if it won't fix everything in old code. One of our big goals is to sort of encourage the virtuous cycling to get teams to do their own work. So as part of that, we send out weekly coverage reports to about 50 teams at Dropbox that sort of gives overall coverage statistics. This is what percentage of your code base is covered, and also tells them things about high priority unannotated functions, like, oh, this function is called 100 times and it's not annotated, or this function you think is annotated, but actually like it's using a decorator that doesn't understand types, and so it's not really, and things like that. Trying to give action items to teams. Now, the question is, does that help? And that's sort of frustratingly hard to evaluate, because it's hard to connect whether the emails exactly are getting people to actually do the work. Teams did request for us to build a self-serve report generator so that they can use it to sort of drive their own work, to go fix all the things and run it and make sure that they're actually fixed. And one time about 6 months ago, we got an email from one team saying like, hey, we found a bug in your reports. We reached 100% type coverage and the report broke. It divided by 0 or something. It's like, oh, we didn't think anyone was actually going to get all the way there, maybe. We never tested that. So we do a bunch to nag people, and then, so those are all sort of social measures. We've also sort of had a bunch of technical measures to try to encourage typing. We have a linter tool that complains whenever you add or change a function and don't put an annotation on it. And we recently bumped that up from being a warning, or being a advice, to being a warning. And in Dropbox's linter system, if the linter reports any warnings, you need to give an excuse for why you ignored it. And it's not hard to give an excuse, but sometimes it's like, OK, well, I'll just fix it. It's only going to take 30 seconds. It'll take 5 seconds to write an excuse. And I don't know, I've never seen anyone complain about somebody's excuse being bad, though. But I always feel guilty when I write a bad one. On top of that, mypy is very configurable, and perhaps excessively configurable. But there are lots of tunables for how strict mypy is. And one of the things we've been doing is sort of gradually ratcheting up the default level of enforcement. So for a long time, mypy didn't by default say that none was not a member of every type. And so we turned that on and sort of gradually added that in. And then we recently made it so that by default, all functions need to have a type annotation or there'll be an error. And you can opt out of this. And as part of doing this, we had to automatically opt out code that doesn't type check. Because if we say, like, OK, here's this new rule that we're adding, then we're going to get 10,000 errors. We need to go disable it in the files. But it turns out that this is a very effective technique for sort of moving the needle. Because if you change the default, most new code is not going to bother to change it back. And if you then sort of every so often go detect, OK, here are the files where we can go turn this on, where it wasn't on, you can sort of gradually ratchet things up and increase the strictness of your code base. So that's all sort of things along the lines of how can we get people to annotate their own code. There's also this question of maybe we can just build tools to annotate code for them, and then people don't need to do work. We can just have computers do it. So there's a pretty straightforward idea for one approach, which is these are programs that run, and they have types. And Python, since it's dynamically typed, carries all these types around at runtime. So you can just maybe instrument your code to look at what types actually get passed to a function, right? If a function gets passed an int, then maybe the type of that argument is int. So we built a tool called pyAnnotate that observes the types at runtime of what gets passed to functions and then inserts them into the source as annotations. It honestly didn't help us that much, though. The output usually required tweaking, so it usually wasn't exactly what you wanted, and so you'd need to go make a bunch of manual changes. And it was hard to get engineers to use it. Other companies have had more success with it. Instagram has reported success using a tool they built called mypy, which does a similar thing. I think one of the differences they did is they actually set it up to run in production, and on like, a 10th or 100th of a percent of requests or something, they'd collect the type information and record that and use it to drive things. We didn't do that basically for organizational and expertise reasons and because we weren't sure it was going to work that way anyways. But I think that is an approach that seems workable even if it hasn't worked for us. So if what I was just discussing, sort of dynamically figuring out type annotations doesn't work that well, or at least didn't work for us. It worked for Instagram, so I shouldn't say it doesn't work. Maybe we can do it based on type inference itself. We have this type checker that has a lot of type information, and so we can use it to try to figure out what the missing pieces are and put it all together. So here, if we have some unannotated function foo, and another function that we are file that we are type checking that passes an integer in, then we can try to say, okay, well, the call site passes an integer in, so let's try assuming that the argument is an integer. And if we do that and type check it, does that work? And what result do we get? And so if we do that, we'll find that it does type check because it's just adding an int to 1, and it returns an int, so we can say, okay, let's say the return type is an int. We've had some success with this and managed to add several thousand annotations using it. And I have plans to push it further. There are sort of much more interprocedural things we can do instead of just looking at call sites. And in our original pass, we were very strict about saying, okay, we're only going to update a type if we are really confident it's the right type and we have a precise type for it. So if we know, okay, it's an int. But if we know that it's just something, so mypy has this concept of an any type, which can be anything. And currently, our annotation tool will refuse to insert that because I figured if we run that, we're just going to get all these basically useless annotations. But the next step is probably relaxing that a bit and saying, like, okay, maybe if half the variables going into a function have good annotations, that's worth putting on. And so that's sort of the future direction for that. Maybe also building a user tool so users can directly use it and have it say, okay, here are like 3 ideas for a type for this function. Which do you think is right? Maybe you can tweak it. So I've talked a bunch about what we've done to increase type coverage, but there's the sort of obvious question of, does this work at all? How have you been doing? Is this been a good use of your time? And the answer is, yeah, it's going great. Here's our graph of how many lines of annotated code we have since we started tracking in 2016. And we started there with like 10,000 lines of code annotated. And this is our main server-side code base. We're at about 3.6 million there and another 800,000 in our client-side repo. So it's great. It's this beautiful up and to the right graph. There's a catch, though, which is that if you take a graph of how long it takes mypy to run, it was also up and to the right. And so this is a full run, checking the entire code base. And at its worst point, it was taking almost 17 minutes to check our whole set of typed code. And this is bad. So we're gonna go look at one more graph. I don't know how useful it is, but I sort of love this graph because it really points out very starkly just like how it's just a straight linear relationship and it's killing us, right? It's a very nice graph to demonstrate the problem. And this is bad because at its worst, we'd become the long pole in our continuous integration system. It takes 17 minutes there, then there'd be setup time, and it'd actually be like 25 minutes or something, which is really bad if it means that every Python change you make, at a minimum, has to go through this 25-minute type checking phase. It became painful to use for interactive development. And fear of worsening this situation limited how hard we could push on growth. You know, if you're at 1 million lines of code and it's taking 5 minutes to type check, that's already pretty bad. And so, like, well, maybe we don't want to add another 3 million lines of code if it means that this tool is going to take 20 minutes to run. So we have a couple strategies for this. The first is an incremental type checking mode. The second is there's an old joke that there are only like 2 computer science solutions to any problem, adding a layer of indirection and adding a cache. And so we took the second one. And then there's a third solution for compilers people, at least, which is write a new compiler for it. So we also did that. So first, the incremental type checking. This, in principle, is pretty simple, though in practice it gets pretty tricky. Because the thing is, the easiest way to compute faster is to compute less. If you have less work to do, then you have less work to do. So the idea here is we store type information on disk. When we run the type checker, we figure out the types of all the functions, and we write it down in a cache on disk. And then the next time you run, you only check things that have changed since the last run. So any module that depends on a module, so any module that's changed, you check. And then you figure out if the interfaces to those modules have changed, things about their types. And if so, then you check any module that depends on them. So this allows you to check just the things that changed and things that might depend on those changes. If there's a code change that doesn't change any function names or types, then you don't need to check its dependencies, otherwise you do. There's an unfortunate snag to all of this, which is that for annoying technical reasons, if you have a cycle of imports where A imports B and B imports A, this all needs to be checked together, all sort of at the same time. And Dropbox has at least one unfortunately big import cycle in its main code base. MyPy itself is also pretty bad. Like half of MyPy's source code is in one big import cycle, and we should fix that. Yeah. Okay, this is an empty slide. There's a snag to all that, though, which is that all works well, and we built that in 2016 or 2017 before the graph got really big. So we were never having users run it actually for 17 minutes. We had this incremental checker pretty early. But there's a problem that you still need to do a full check at some point. And the changes that you get when you do a branch switch or you rebase are often really big. I mean, we have a lot of engineers, and there are going to be a huge amount of changes basically every time you do a pull that have nothing to do with what you want. And so if you're having to do all this rechecking every time, that's still pretty bad. So the solution to that is we have our continuous integration system generate type information every time there's a commit. It goes and runs a full check, and it writes down all of the types, and then it populates a cache that's shared between all the developers at Dropbox that gets populated about 20 minutes after each commit. So every time you rebase or branch switch, we have scripts that will go download the most recent cache and use that to sort of quick start. So you don't need to run the whole check to build your cache. You can just download it, produced once for everyone. This works great. Unfortunately, it's not open source. And it's not open source because there are any secrets. It's like 100 lines of Python and 50 lines of Bash or something. It works great, but it's unfortunately sort of too dependent on the minutia of the CI system and the build system and the source control to be code that can be released nicely, right? So it's going to be different with every sort of combination of systems. We have some decent docs for how to do it in our main docs that talk about how to use a remote cache. I'd be really curious if anyone else has actually tried to do this. I think Facebook did back when they used mypy, but then they built a competing type checker, and so probably don't anymore. this whole cache warming thing has a lot of fiddly performance engineering work to make it all work well. It turns out it's very important to use a good compression algorithm. At one point, we switched from gzip to LZMA, and that sped things up by 30% or something downloading it. At one point, we switched to, instead of, originally, we'd write these caches as just a bunch of JSON files in a directory tree. But it turns out that OS X really doesn't like creating and accessing tons of small files. OS X's file system is awful. I have so much of my life has been dedicated to fighting with OS X's file system in the last year. But so to solve that, we switched to using a SQLite database, which is the advantage of only being one file, and the disadvantage that we are now simulating a file system in a SQLite database. But, and we sort of spent a long time investigating more optimized cache formats. Can we load these caches faster? Can we read them quicker? Can we decode them? And I think there's some space for improvement there, but it's minor. There's still a bunch of downsides here, though, which is these incremental databases are still a lot of data to load from disk every time. A module is kind of a big target. Like, you have modules with, you probably shouldn't, but we have modules with 10,000 lines of code in them, and rechecking that takes a while. And we have these big import cycles and need to reprocess them all together. And our biggest import cycle is also our baddest code, right? So, and whenever a file's dependency change, this system requires you to fully reprocess everything about the module. And so that's all pretty slow. So we built a new approach to that, which is our incremental type checking daemon, or mypy, that's been available for a year and a half now, which is our solution to all the problems in the previous slide. And so the way that the daemon works is it sits around in the background, taking up too much memory, but keeping all the syntax trees and types of everything you've processed in memory. It then, once those are loaded, it will compute the dependencies of every function and class. So as an example here, it will see that this eggs function in module B has a dependency on the foo function in module A. And so it sort of writes this down as b.eggs arrow a.foo, and in a sort of dependency tracking. And then when something changes, instead of rechecking all the modules that depend on it, we can be much more fine-grained. We can recheck only functions that depend on it. So here, if the type of a.foo changes, we can just recheck b.eggs. So, yeah. So how does this work? Well, first, like I said, we compute the dependencies of all the functions and classes. Every time it's run, it figures out which files are changed. By default, it does this by sort of statting every file, but it's also possible to integrate with something like Watchman, so it will be notified, okay, here are the files that have changed and can be rechecked. When it rechecks it, it figures out what has a change that was important. And important basically just means that the type of something changed. If you just change the body of a function, that's fine. Once that's done, you find everything affected by these changes, and you recheck just those functions. This turns out to be some pretty gnarly code because mypy was really deeply not designed to do this sort of thing. It was very much designed to be a run once thing. And so updating everything is hairy but works. And then you repeat this until you reach a fixed point. Like with the previous one, we can speed up startup by loading from a remote cache, which helps a lot. The upshot of all this is that our P75, which means that 75% of runs are faster than this, if the daemon is already running, is less than a second. 700 milliseconds is what 75% of runs of our type checker take. Unfortunately, it's a little worse for when the daemon starts. It was 52 seconds the last time I gave this talk, but now it's 70 seconds. And so I probably have more performance engineering in my future. But the most gratifying thing about this is as soon as we rolled out this type checker that could run in a second, the number of times people ran the type checker according to our telemetry went up by like a factor of 10. People use the type checker way more when it's way cheaper, which is really gratifying because it showed that people really wanted to be using this as a big part of their workflow, and we were making that possible. The problem is this is still kind of slow for non-interactive workflows when you're running it in CI or whatnot. And every so often, there'd be something where the incremental cache system would break, and then the tech lead of the developer effectiveness team would come over to my desk and be like, hey, how long until this is fixed and you stop taking 25 minutes? Empirically, it would take about 2 hours before he'd show up at my desk, so that was my SLA for fixing it. But the problem is it only checks 2,000 or 3,000 lines of code a second, sort of historically. And when you have 4 million lines of code, that's bad. So then the question is like, okay, well, it's only checking 2,000 or 3,000 lines of code a second. Why is that? Why is it so slow? And the answer to that is actually really simple and a little disheartening, which is because it's written in Python. We like Python, and there are a lot of advantages to being in Python. It makes it much easier to interact with the community. It means that you can write plugins in Python, which is nice, especially for community reasons. It's just a nice language. Facebook solved this problem by rewriting a new type checker in OCaml, but that seemed drastic to us. So why is it so slow? Because it's in Python. Well, there are a bunch of things. One is interpreter overhead. It's not directly running code. It's an interpreter loop that has to read opcodes and dispatch, and there's a bunch of stuff there. Sort of more important, though, is that accessing an attribute or a method is multiple hash table lookups. If you write foo.bar, it's going to do at least 2 hash table lookups and maybe some allocations, and it's just this whole big process. And in general, layers of indirection everywhere. So the question is, well, why is this all true? Why is attribute access a hash table lookup? Why are there all these layers of indirection? And the answer is because Python doesn't have types. So the history lesson, historically, in languages like C, static types were all about helping the compiler, right? Early C programmers, it didn't have types to find bugs, which can be seen from the fact that it doesn't really help find bugs all that well. It's just about helping the compiler and does very little safety checking. It's basically just to help the compiler determine data representation. So in C or whatever, if you have a struct foo with an int and a car pointer in it, it will make the struct layout that's a tag at the first byte and then 8 bytes later data, and just there in memory. And if you write code to access it with p arrow data, on x86 it turns into one instruction, right? And instruction count is not a direct proxy for performance, but in C, accessing an attribute is 1 instruction, and in Python, it's more than 200. And that 200 includes dependent memory accesses, indirect branches, all sorts of things. And so there are a lot of things why Python runs slower than a lot of other languages, but this is the big one. It's this sort of data representation stuff. And now, PEP 484 and mypy static types were very much mostly designed not to help the compiler, but to help programmers to do safety checking. But that doesn't need to be true. You could imagine that you could use the types. And in fact, PEP 484 actually says this. It says, using type hints for performance optimizations is left as an exercise to the reader. So we went ahead and did that exercise. MyPy itself is statically typed, basically all of it's typed. And so we had this idea of we could write a new compiler for type-annotated Python that takes advantage of this type information to generate efficient code. And now there's this question of okay, well, you're a bunch of compilers people deciding that the only solution to your problem is to write a new compiler. But the thing is, just because all you have is a hammer doesn't mean that the problem you're solving isn't a nail. So this was sort of started by Yuka Ledesalo as a side project, a Hack Week thing. It was sort of unfinished business from his PhD thesis, which was designing a Python-like language that would be typed and compiled. But that eventually morphed into the mypy checker for Python itself. And so now we've sort of come back and finished the unfinished compiler part of it. So we built a tool called mypyc. It compiles a subset of Python with what we call strict semantics. It is essentially a language variant because there are different behaviors. The most salient one being that types are enforced. If you pass something that isn't an int to a function that expects an int, it will raise a type error at runtime. It uses mypy as a front end to do the type information, and it generates Python C extension modules, which is the bog standard way to write Python libraries in C that's sort of very heavily used by a lot of programs. And we just use those APIs, and we generate modules that are loaded by CPython and can interoperate perfectly well with code that's running in Python and with other Python libraries. Now, the question, what makes this different? This probably isn't the first compiler for Python you've heard about. And another way of asking about that is like, what about the bodies, right? What about all the people who've died trying to do this? Or like not died, but who we're ignoring. And so there are a couple answers to that. Python, if you don't translate to sort of their dialect and type system, you probably won't get big speedups. It'll avoid interpreter overhead, but not much more than that. And we don't want to translate to their type system. We want to use the standard PEP484 type system. PyPy is a tracing JIT, which is great for certain workloads, and in our testing was not great for our workload. Piston, Unladen Swallow, which are both traditional JIT efforts, Piston formerly done at my employer, sort of chose the full language support hill to die on, which is to say, you say, okay, we want to be compatible with all of Python, and then you spend all of your time making it compatible and none of your time making it fast, and then your employer decides to stop paying you to work on it. So we're not aiming for exact compatibility. We're sort of aiming for a subset that plays nicely with types. And last time I gave this talk, I had to have a proviso that there are some really embarrassing gaps, but we've mostly closed the worst ones, like functions can now take star args, which they couldn't last time I gave this talk. So what does the code we generate look like? So first, sort of diving into the data representation bit of it. If we have a class foo with attributes tag and data, we will generate this struct, just a C struct that's a Py object and has in it just attributes for tag and data. Integers are stored unboxed when possible, so you don't need to allocate a separate Py object for it using a traditional scheme where you use the low order bit to indicate whether it's a pointer or an integer, which is venerable and hacky. It uses a traditional object-oriented approach for method calls, which is that objects contain a pointer to a virtual table that is a table of their methods. And so the table here would point to a table that has a pointer to f. And so then the question is, well, how well does this work? And the answer is real well. This is how long it takes mypy to type check our code base. I had truncated the graph before to leave everybody in suspense, but we sped up mypy by like 3.7 times or something. It basically solved all of our near-term performance problems. We've been using it all year. We were using it well before I updated the thing that generated this graph to use it. Now, that doesn't mean that our problems are through, because if you go look at the same sort of graph here, you can see our code annotated is still getting slower, and so is our runtime. There's a bit more of a bump in the middle because we rewrote a big component to be more correct and a little slower. We weren't trying to rewrite it to be slower, just more correct. So what's the future then of mypyc? And so we built it with a sort of narrow purpose, which is as a mypy accelerator. And it was important to us that we be able to say, okay, this is worth doing just because it'll speed up mypy. And when I say important, I mean sort of to our boss, right, who is paying us to do it. Because we sort of didn't want to try to be pitching any of these big, ambitious projects. We're like, oh, we're going to compile all of Python and make it tons faster. But even though our goals were originally pretty narrow as a mypy accelerator, it doesn't probably always need to be a mypy accelerator. And so the last time I gave this talk, about 4 months ago at PyCon, I said, I think our next plan is I have an intern this summer, and I'm going to make him get Black to compile with it. And so I'm happy to say that we have Black compiling. Unfortunately, the Black performance numbers are much less impressive so far than the mypy ones. It speeds up Black by like 25 or 30%, though I think there's still some work for a bunch of fixing and profiling and performance engineering to happen there. But things are coming along. We can compile quite a lot of Python code now. And sort of the next step for me is trying to get it actually integrated and deployed at Dropbox. And there are a lot of question marks there, but I'm optimistic. This is all on GitHub. This has all been open source the whole time. And I think next week it's actually going to get merged into the mypy repository proper instead of being on its own. not because mypyc is as ready for prime time as mypy, but because it turns out that like there are just a bunch of technical reasons that make it a huge pain to have a self-hosting compiler split between 2 Git repos. Really frustrating for a lot of annoying reasons. So the TLDR of this is we're at Dropbox checking 4 million lines of type annotated code, and usually we're doing it in a few hundred milliseconds. And we've accomplished that through bothering people to type their code, increasing automatic enforcement, automatically adding annotations, and then a lot of really detailed performance engineering to sort of keep up with all of our success. All right, thank you.
Question?
Yeah.
So I think probably most of us here have some faith that like annotating type leads to better code. Do you guys have any metrics that any clever metrics maybe that you've,
We don't have any anything that isn't anecdotal, and I'd be really interested if anyone has found a good way to measure this. We have a lot of good anecdotes that make us feel pretty good about what we're doing, which is every so often somebody has a file that wasn't type checked, and we have a sev, an outage, and they're like, oh, here's a sev 0 that cost us $1 million that would have been prevented if that file was type checked. And so that always feels kind of good, and also kind of bad, because maybe we should have gotten that file type checked by now. But we have that sort of thing. And then we have a lot of anecdotal information about using it to drive refactoring and Python 3 migration, where it really does seem to help a lot.
Hi. So I teach Python.
Okay.
When should I teach type checking?
Oh, that's a good question. Are you teaching it to people as their first programming language?
Sometimes.
Okay. Yeah, this is a good question. And I have a different opinion than, I think if you ask everyone on the mypy team, you'll get different answers. I can say Guido, who works on this project, thinks you should teach without types. I don't know. I come from a typed background and think introducing types early is good. The only main snag is it's annoying to explain that it's a separate tool. Though you could probably build some sort of tooling that sort of runs them together and makes that easier.
I do it in Jupyter Notebook, and then there's like a little thing you can add, like a little annotation that'll check it in the notebook.
Okay. I've never tried doing types with Jupyter Notebook. That's interesting.
I was curious, you mentioned that speed was one of the main issues for the type checking CI portion.
Yeah.
Why weren't you able to turn it into a distributed CI build?
Sorry. Because it doesn't parallelize very well,
Okay.
basically. Yeah.
So a question around types. So coming from Java, you think of classes and things, but types in Python, we mean pretty much primitive things. I'm just curious.
No, they also mean classes.
Okay, so
Yep.
Okay, great.
And classes and tracking the attributes and methods on classes is a huge important part of it.
Do you guys have a strategy for turning type comments into annotations?
Yeah, there's a tool.
Yeah, there's a tool.
I think it's okay.
Which one?
I don't remember. Wait. No, but that's for taking, isn't that for taking? Ivan Levkivsky wrote a tool. I don't remember its name.
I'll search for him.
I think we used it at Dropbox to convert our type annotations in the client or our type comments into annotations.
Yeah, because we're starting to get rid of Python 2.
Yeah, and I think it's not perfect, but it's good enough to be worth using.
Yeah, cool.
Yep.
Hi, are there any performance issues to be aware of if we're converting untyped code to typed code? Maybe specifically if we're returning unions or things that might accept multiple types?
Yeah, sort of. What version of Python are you using? 3.8. Okay. So there's an annoying default behavior in Python, which is that the type annotations are actually evaluated at runtime. which can have a usually not significant but minor performance cost, and it mostly is paid at startup. But Python 3.7 introduced a thing to disable that called from future import annotations, which makes it so that annotations don't get evaluated at runtime. And this hopefully will be the default eventually, and probably should have been. But if you add that, then you won't have any of this. And also, I don't think it's that bad. Like, we don't worry about it in mypy.
Hi, Michael. Thank you for your talk. I'm curious how you lobbied your leadership and engineering leadership to advocate for checking for types without maybe having the same rigor of metrics for tracking exceptions and things like that.
Yeah.
It seems the metrics were mostly focused on the performance side of things rather than the outcome.
Yeah, so a lot of our stuff is from our developer productivity surveys. Sort of our main focus pitching things has been on developer productivity more than bug reduction, because because at least using the standard metric by which we measure any developer productivity thing, which is developer surveys, we can use that. And I think we've had decent success at that. But mostly the battle to convince people that it was a good idea was won before I got hired. And so I don't have as much context on all of that as I could.